Hello, is my voice audible?
Yes, sir.
Okay, thank you. Screen is visible, right?
Yes, sir. Visible, sir.
So, welcome to the coursework for signal processing for millimeter wave communication for 5G and beyond. And this is the assignment for week 8, and it is for the previous year's coursework. Like the assignments for previous years. So, the first question, let us start. The first question: if we provide defined data points like QPSK constellation to each of the elements of antenna array in millimeter wave system, the corresponding beam pattern will depend on the four options: antenna array spacing, option B direction of the signal departure, option C is phase of the constellation points, and option D is all of the above. So anybody to answer this question? Okay, so
Sir, all of the book.
yeah, it is all of the above. So let me solve it. The first one, the first one says antenna beam pattern and on which it depends. So from the beginning of the lectures, it is mentioned that the beam forming is done by the two things. First is array processing sort. Right. How direct processing depends here? This depends on antenna array spacing. First, and the second point is angle of departure. The third point also can be like number of antenna arrays element. These three. These three can be done for doing the beamforming. Like angle of departure depends on both of them. So beamforming also depends on both of these. And for the second point, we have no control. Angle of departure, we have to know in where the receiver remains. At that direction, we have to do the beamforming. And so let us go back to the question number one. So it says the corresponding beam pattern will depend. It should obviously depend on direction of signal departure, because that is the direction where we should do the, in that direction we should do the beamforming. Number one absolutely depends, because it is the antenna array spacing and the beamforming depends on that. And phase of constellation points, it is very much important, because if your constellations are complex, then at this point the phase of every constellation point, like if I think here QPSK, for QPSK it will be, the constellation points are like 1 plus j, minus 1 plus j, 1 minus j, and 1 minus 1 minus j. So each of them has a different type of phase, And whenever these constellation points goes to the antenna arrays, so this individual phase will affect the beamforming, because we know there is an array manifold vector 1 e to the power j phi e to the power 2 j phi. In this way it increases, so plus sums of this phase will get attached here. So this will depend on the constellation also. This was not the case for sub-6 gigahertz. In sub-6 gigahertz, what we do? This sort of thing, and we do not do any beamforming there. So this is the special case that constellation phase also depends how the beam forming beam pattern will change in this case. So the first question is option right answer is option D, all of that. This is the right option. So let us go to the second case. A millimeter wave MIMO system has a total M data stream being applied to the phase shifter as input, and there are N receiver antennas in the receiver side. So there is one more point, that suppose the antenna array in transmitter side is using 6 antennas, like NT, that value is 6 for transmitting data from a particular data source to obtain beamforming techniques. So the number of directed beams will be. So how many directed beams can be created for this sort of technique? So let me draw the picture first and then I will ask the question. So there are S1 dot and this is SM, because there are M data streams and each of them are like this. Covering the points, we provide the phase shift here. And there are also this sort of thing, and to optimize the number of antennas we can do this sort of thing. This goes here, gets a adder, from here it also comes like this, and all the first elements got added this, and it is transmitted from the first antenna. Similarly for the second, here comes, from here one middle point will come, and here it comes and it got added, and for third here it will come, it comes here, it got added, from here it also one term comes. So like now it is said this sort of thing, I have M data stream. That is the question. And in the receiver side, there are n number of antennas. Suppose there are n number of this sort of antennas. So the question is, here will be some sort of beamforming for the first, for the second, for the third. Like millimeter wave, we do beamforming, and in the directed beam, we find the particular receiver. Suppose this is the first receiver, the second receiver. In this way, there are n number of receivers. Okay. So with this sort of thing, how many beams we can create? Like suppose there are n receiver, but I cannot generate that number of beams. Probably some user is not getting any beam. That may happen in this case also. So the question is, how many beams can be created for this sort of thing? So see, For each of the antennas, what we do from the first and last, we add up. So this sort of constellation will be like how many? M number of M. So this M and here will be NT. Suppose there are NT number of transmitter antennas. So this M should be nearly equal to NT here, if I think in that way. So how many beam patterns will be generated? For this is a bulk of antennas that will do a beam for me, and this is sort of first beam, and this is attached to this. For the second beam there will be attached to this, and for the mth, for this phase shifter there will be another beam steering effect. So total number of beams will be M. So the number of directed beams will be A, the option A, and it is M, because there are M data stream and it is applied to the phase shifter. I don't know from where it is coming, but for the phase shifter case, for beam steering case, we are providing the feed to M data stream. That is the case here. So that is the reason there will be M number of directed beams. So this is option A. So A. The case is, it is sort of broadcasting thing. See, from here some data is coming, from here some data is coming, and all these data are going through the single antenna and is getting fed to one of the receiver antennas. The same thing, each beam is feeding another receiver antenna, and the data is here is s12.sm. All the data are contained here. In the same beam we are sending to the particular one direction. So there will be M number of streams. So let us come to the question number 3. 1 minute. The question number 3 says, in a millimeter wave system, the beam steering in the transmitter side is done by, first option is rotating the antenna position, second option is applying relative phase shift in antenna array elements, option C is by switching the antenna array elements, and option D is none of the above. So why do we think that other options, which option is correct and why not the other options? That is the main thing here. So this is question number 3, and it is a millimeter wave system. So more precisely, this millimeter wave system, if I say, it can be used in two senses. The first thing that is well known from the Second World War time, that is radar technology. Another thing is approaching right now, and it is using this millimeter wave in your handset. So in radar technology, you can rotate your antenna and also you can switch the antenna array elements. Because this radar system is dedicated for only this purpose. Like we have to track some particular moving element, and for this This is the cost. Your hardware is very big, but it tracks nicely. However, for handset case, it is not that sort of tracking. Like, moreover, it is from a cell tower. We are just receiving some sort of signal, and the sole purpose is to avoid the sort of things like interference, provided nobody is trying to jam all these things. And beamforming, take the advantage of beamforming, so we can neglect the freeze path loss thing, all this sort. So if we think for a mobile system, we use a rotating antenna. That means your handset has an antenna, and that antenna is can be rotated inside your mobile to find the exact direction. So this is sort of tough problem. So rotating that antenna is not possible for this your handset. Also, you as as discussed earlier, switching the array elements, that is not done. Here we use isotropic things, isotropic antennas, and then we just use perturb the number of antennas and also spacing. This gives relative phase, and this sharpens the beam. So switching means we keep one of the antenna elements off and another on. That is very costly in terms of small hardware devices. So these two options cannot be the option for a handset. So the option is applying relative phase shift in array elements, and this relative phase shift depends on antenna spacing. And also you can think like you increase the number of antennas, that sharpens your beam. So these sort of things can be done for beam steering in transmitter side in a millimeter wave MIMO system for only cellular type of system, like your handset, mobile handset, all these things. But option A and C, probably I will say they are dedicated for the data system. So the correct option is option B. Let us go to the next question, the fourth question. The fourth question says, in a millimeter wave MIMO system, the advantage of MIMO system is claimed by sending every beam pattern of transmitter side to each antenna in receiver side. That is, I will send a dedicated beam from the transmitter side to each of the antenna in the receiver side. The option B is mixing weighted sum of original data vector in baseband and applying it as input signal vector of steering vector. Option C is sending a particular input data to a destined receiver antenna using beamforming techniques. And option D is switching off every antenna while one of the antenna is transmitting. Like I just only sending one of the beams at a time and all of the other antennas are off at that moment. So to answer this question, I will first ask you uh, the advantage of MIMO system. What do you understand by the advantage of MIMO system? Anybody here?
To increase the capacity of the system and decrease the probability of error,
Okay, so
diversity and multiplexing.
okay, so uh, diversity again, how can you achieve from which side here, like transmitter side or receiver side?
We can achieve by any like transmit diversity or receive diversity.
Okay, and capacity, how do you say? Why the approach? How can you say the capacity increases for my system? Like why not in CISO system? How you can get that?
By creating multiple streams of data by
Okay.
MIMO.
So here we are using millimeter of sort of thing, right? So here is no that sort of mixing. So in MIMO system for sub 6 gigahertz, so this is the sub 6 gigahertz model. So I have some sort of device and the data is going like this, and when I receive the data inline, it comes to this end. This is a MIMO system. Like your user is one, user is fixed, you can think. But the thing is, we increase the number of antennas. Always remember that. MIMO system does not mean your user are different. It can be, that is multi-user MIMO. That is a different case. So for a single antenna case, in a sub 6 gigahertz, like the same signal, if you send to into two different antennas, so I can say probably H1x1 and H2x2, H1 H2x1. Simple advantage I am showing, like see, suppose first time you are sending from this and there is only one receiver antenna and there is only one path H1x1. So suppose this H1 is very badly affected and H1 is supposed in 10 to the power minus 16 this term. So at this case, suppose this HT is very high. So this side probably will take H2 plus H1 into X1, and for this it is easy to detect. Why? Because there is a W1 term. So if it was H1 and X1 plus W1, this SNR is what? For this SNR will be H2 plus H1 square by X1, sorry, mod of X1 square by W1 square. But for this it will be mod of H1 square by W1 square, whatever this is sigma square and X1 square. So if this H1 is very low, at that case you will not get to recognize the signal differently from this noise, because noise is very high and comparable to the signal. But probably for this case, as H2 is better, at that case you can detect the signal easily. So probably that is the one of the advantage of MIMO system. But moreover, we can increase the capacity. Like we increase the number of antennas here, so our SNR increases in this case. This SNR part increases, and if the SNR part increases, we know capacity is equal to 1 plus SNR. So this is the advantage, to increase the capacity. Also in terms of BR, if we can think that way, we can improve the BR also, bit error rate and capacity. So these are all the advantages of the MIMO system. But for millimeter wave, what we do, We always do the sort of beamforming thing. Like this beam is dedicated for one of the antennas, the next beam is dedicated for the next antenna for the same user. Probably you can think they are attached here like this, but this beam is dedicated for this antenna and this beam is dedicated for this antenna. So there is no that sort of MIMO. Like this H1 X1 is completely different, H2 X2 completely different, and they don't get added. So somewhere to get the advantage of this capacity equation, like if we want to increase high data speed, we need to mix up the signals like this, like H1 X1 plus H2 X2, and increase the capacity of the system. To do that, what we do, we mix the signal before we start to transmit. Like this beam will contain S1 X1 plus S2 X2. But what is the advantage here? We do not need to do the channel estimation here. Probably the weighted sum for a 2 cross 2 antenna. Let me draw. H1, H12, H21, H22. So before transmitting any data, we have to do a channel estimation here for the MIMO case. Because we need to know what are the parameters H11, H12, H21, H22 from subscript cards model we have already discussed. So this channel estimation part, you have to know what is the coefficient H11, H12, H21, H22. But suppose there are some vectors and we are doing this sort of thing, this before we transmit to the air. So the signal is like this, the signal is coming and the signal is coming, and we add up this signal, these two signal with some weight. It is W1 and this is W2, and it is S1 and S2. So it becomes W1 S1 plus W2 S2. Another thing is comes like so this mix up, like the first thing y1 is equal to h11 x1 plus h12 x2, sorry, this is h11 that is multiplied by x1 and h21 x2. This mixing we do before the beamforming starts. So these parameters we already know, we don't need to estimate in a millimeter wave. But we can take the advantage of the MIMO system, like increase the capacity of the total system by doing this mixing. So that is the reason we do the mixing first and then feed that signal for the beamforming purpose. So mixing is also done. Millimeter wave is also used here. What is the advantage? Like we can use the free spectrum there, and also beamforming can be done. If we try to use this sort of thing in millimeter wave, this beamforming will get interference and the advantage of millimeter wave will be gone at that case. So that is the reason we do this sort of mixing. And so that is mixing weighted sum of original data vector in baseband. So we do the mixing of weighted sum of original data vector in baseband type of thing and apply it as input signal vector of the steering vector. Like we take that signal, that mixed signal, and do the beamforming on that input signal vector. So in the same case we get the advantage of free spectrum MIMO system, and it is also millimeter wave system, and beamforming, particular directed beams can also be generated. Both the things can be done in the same system. So this is what millimeter wave MIMO system is. So correct option is option C. That is, sorry, option B. Correct option is option B. Let me write it. Okay, so we go to the next question. The fifth question is the RF decoder in transmitter side is a fat matrix, a tall matrix, a full rank matrix, or any of the above. So, anybody can answer this question? Like, what is the answer for this?
Full range matrix, sir.
It is a tall matrix, right? So, as I discussed, so there is some data stream that is coming, M data stream probably. And this is YT. Suppose there are NT number antennas. For each of the NT antennas, there will be a bulk of antennas, like to do the beamforming. Like if I want to do a beamforming through this antenna will depend on, suppose, in one NT1 number of antennas, like isotropic NT number of antennas. Like if I want to do a beamforming this side, probably I need 10 antennas here for this sort of beamforming. So this NT is like 10 into NT. If I take for each of the antennas to do the beamforming here, I take 10 antennas for the beamforming. So if there are total NT number of beamforming here, if total number of beamforming is NT, so I will need NT into 10, that many number of total antennas. So this NT will be probably equal to M into 10, that many number of antennas. So the received vector YT, it will be the data vector into WRF. So this WRF, suppose S has a dimension of M cross 1, as I have discussed, and in this YT, it will have a dimension of what? M into 10 number of rows into 1. So this WRF should have M cross 10 into M. I mean 10M cross M. This sort of dimension WRF will have. So this is 10M cross 1 is equal to 10M into M into matrix M cross 1. As per the rule of multiplication, it remains the dimension constant. So WRF, this is the RF decoder in the transmitter side, and it has more number of rows. That is why this matrix is a tall matrix. Like the structure will be number of rows is more than number of columns. So that is why this is tall matrix. So the right option is option B.
So its size is WRFT size is NT cross M, na?
Yes, but I am saying, suppose this NT is 10M in that factor, right?
So NT, there is one assumption, na? NT that is NT is greater than M.
That is the reason why you
Yeah.
need, why should be NT greater than M? Can you tell me?
For the beam forming purpose, na?
Yes. So if there is one antenna, probably there are NT. So for each of the antennas, I need multiple small isotropic antennas, right? That is why I need more number of antennas, right?
Yes.
Okay. So that is why it is a tall matrix. Option B. Let us go to the next question. It's the question number 6. The digital precoder in transmitter side for millimeter wave system is used to. So why we need the digital precoder? And why we need RF precoder? And what is the advantage of taking the digital precoder? Anybody here?
And digital precoder for that splitting, you can say, for distributing the data to various beams and
Various beams in the sense, if you say for the various beams or beam phase shifter.
for a single beam, actually, we whatever the data sets we are getting from different streams, we want to distribute that data
So why we want to distribute the data? That is the question.
for getting MIMO feature, actually.
Yes, yes. So the correct option is option C for the sixth question. And RF recorder is the record for the beam steering purpose, and beam forming is done by that antenna spacing and number of antenna elements. Like you have the beam, you want to shift the beam, use the RF recorder, and you take the advantage of MIMO system by using digital recorder. So that is the whole system. So question number 7. From the implementation point of view in hybrid beamforming.
Sir, excuse me, sir. The answer for the 6th question is?
Okay, the option C. For 6th question, the option is C.
Okay.
Seventh question. From the implementation point of view in hybrid beamforming, where does the phase shifter lies? In the RF domain, in the analog domain, in the digital domain, or none of that? So, what is the correct answer here? Like,
RF domain.
okay, so this is also straightforward from the lectures. So, question number 7. We actually think that we are doing the beam steering in the DSP domain. But it actually is implemented in the RF domain. The correct option is option A. The next
Option?
question,
Sir,
option
option
A.
C, sir?
Option A.
A,
Impl-
RF domain.
yes, option A,
Okay.
not C.
Okay.
From the implementation, it is A. So the next question is for a millimeter wave signal input multiple output system, single output multiple output system. The equalizer part is done in LNA phase shifter in DSP domain after that, or both A and B. So the correct option will be like both A and B for the 8th question. Question C is C. Answer is C. It is correct. It's, yes. The question C, the C is the correct answer. So question number 6 is the correct answer. So the eighth question is how the equalizer is done in millimeter wave. So the option is correct option is option D. That is, first it is done in the LNA and second it is done in the phase shifter. Why? Like suppose you have something y is equal to, this is a one of the channels, h1 star, h2 star dot h something, and it is getting multiplied with xn plus some noise is getting added here in a number of receiver antennas. That is why. So each of them has a particular gain. So if I just reverse that gain by the use of LNA, LNA provides h of 1 star mod of this value, and the phase shifter provides what is the angle e to the power j omega 1 star. Probably this is the phase corresponding to this complex number. So if I multiply by this will be like cancelled out, and it will come like mod of x square, like just the opposite thing, like we multiply by the conjugate of this. So if it is h1 star, we just multiply it with h1 star will be multiplied with h1. So we have to find what is the gain of h1 and what is the phase of h1, and we just multiply the signal h1 star xm with this sort of LNA, and this is the LNA gain, and this gain comes from here and phase from here. So it cancels out and it goes like mod of h squared xn plus w, and then we divide it by xn plus w by h. Probably you can use this technique. So the things that are used, LNA and phase shifter. Option D. So next question is option number 9. Question number 9. The question is, for a millimeter wave MIMO system that has n input data stream, like total number of data stream is 5 before the precoder into the initial of digital precoder. I mean actual data stream is 5 here, and it is going to be fed in the digital precoder where it will be mixed. And the next statement is the number of receiver antenna is 6. So in the receiver side the NR is 6. So the question is and also it is given the equalizer matrix in the receiver side has a dimension of 6 cross 6. So the question is, how many number of phase shifter is required in RF side to design the equalizer given all this information? So what is the answer?
$36.
Yes, it is 36 for the question number 9, because there is 6 cross 6 elements, and each of these elements corresponds to the particular channel coefficient, like we discussed in the question number 8 here. Each of the coefficients for a, if it is a 6 cross 6 precoder, there will be 36 element, and for 36 element you have to provide 36 phase shifter. So that is the reason for question number 9, it will take 36 phase shifter. So the correct option is option D. Option D. You need 36 phase shifter for a 6x6 decoder equalizer design. And the last question here for today. Suppose a millimeter wave system has 5 input data stream in the input of a digital precoder, and each of the data is coming from a QPSK constellation. So QPSK constellation is the constellation point, and there are 5 input data stream to the for the digital precoder, like it is before the MIMO thing happens. So number of elements in the search space for ML detection algorithm in the receiver side will be how much? So what is the answer for this question also? So anybody to answer this question? Okay. So how many input data stream? 5, and each of the data stream is coming from a QPSK constellation. So what is the millimeter wave system I can write in a short form? This is y is equal to hx plus w. This x is the data stream, so x is equal to 5 plus 1. So in the output, what I need to find out, all these 5 datas that has been sent through this system. Suppose this is a millimeter wave system black box. You can think this like this. This is a short filter. Whole thing is a filter. I provide some input x and it gives me y. And in the end, we have to find what was the x was there. So x has 5 elements. First x1 dot 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 x5. So x1 has 4 possibilities. Why? Because it is coming from a QPSK constellation. That can be 1 plus j, 1 minus j, minus 1 plus j, minus 1 minus j. So how many possibilities are there? 4 possibilities. So for only x1, I have to find whether it is 1 plus j, 1 minus j, minus 1 plus j, or minus 1 minus j. So there are 4 possibilities. Similarly, for x5 there will be 4 possibilities. So if I want to find between the set x1 and x5, how many possibilities are there? For x1, 4, and for each of the x1 there are independent 4 possibilities for x5. So in the same way, if I think there are 5 data streams, so it will be 4 square, because I have taken 2 data stream. If I think similarly, the question is said there are 5 data streams, so the search space will be 4 to the power 5. For the first there is 4, for each of the 4 there will be another 4. In this way it comes like each of them is 4 possibilities there are, so that is 4 to the power 5. So if I calculate 4 to the power 5, that comes 1024. So
Sir, can you
that,
explain this part again? How you got 4 square?
okay. Suppose the first thing is 1 plus j. Okay. Probably. It is QPSK, so it can be any of them, right? It is clear to
Yes,
you?
sir.
So how many possibilities are there? 4.
Yes.
So for x5 there will be another 4 like this.
Yes.
So suppose for 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 the first point I somehow detected this, but this is completely independent of this, right?
Yes.
So for the second there are still 4 possibilities.
Yes.
So let me draw it again.
Okay, 4 into 4 into 4 into, yes.
Yes.
Got it, got it.
For each of them there is another 4. Okay. So that is the right option. Option is option B. Q10. This is for option 9. Option D. So this is all for today. So anybody has any question?
Excuse me, sir.
Tell me.
Option, question number
Your
10 option.
question number 10. Okay. What is the
Option
problem?
C or B, sir.
Question number 10. It is option 1024. Option number B.
Okay.
Okay. Thank you. We will meet in the next list.
Thank you, sir.